Chapter 4, Section 7, Polynomials in Several Variables. We're going to evaluate polynomials, look at like terms and degree, and addition, subtraction, and multiplication of these things. So the first part they're going to talk about is the degree, or, well, first they start evaluating. If we put in actual numbers for the variables, how do we evaluate that? So that's the first part. They usually start each section where we have this new kind of polynomial they're talking about, right? So we have here polynomials, and we're going to evaluate them for certain values for the variables. In this case, there's multiple variables, so they give us x is equal to -2 in this case, and y is equal to 5. Well, the best way to do this, and I've seen students not do this by habit, and you can have some problems when you're writing down your work. It's a very good idea to put parentheses around, or put slots with parentheses for the variables, and then fill in the number for the right slot for that, right? So here's where x was. We put in -2, and they just went blue with 5. I would put that 5 in parentheses 2 with a squared around it, or to the 2 power, and so on. Remember order of operations issues, and then you can evaluate this. In this case, it ends up to be a -8,052. They give us an example. This is a formula for surface area, and if you remember how to get the area of a circle, you know, if you think about this cylinder here, this pop can, there's a circle on top, right? So you have this is the area of a circle, 2 pi r squared. So if you know the radius, I know the area of that circle. Pi is really a ratio. The circumference divided by the diameter of any circle gives you this number pi, and which is 3.14 as an approximation for it. And the reason they use a symbol is that they've never found any repeating decimal. They've never been able to make this into a rational number, even though they've taken it out millions of digits right at the decimal place. So here is a more accurate measurement for pi, or value for pi, excuse me. Well, this formula, if you think about this, like especially like rectangular prisms, or something that looks like a box, if I take the area of this, I'm going to end up with the amount of square units in this circle, and then I'm going to turn that into cubes by putting that same unit, just chopping this thing down here. If I chop that one unit down, basically I'd have one row of all those cubes, right, that are measured if I looked at them at the top, and so on. Well, that's what they get here. They take that height, and so on. That's how to get a volume of this deal. This is surface area, which is another issue too, is that I have this surface up here is the area of a circle. The bottom is going to be an area of a circle. And if you cut this can, let's say I took the top off and the bottom off, and I cut that can and rolled it out, I have a rectangle, which is going to be, the one side is the circumference of that circle, and then this side, so I have a rectangle, and that's where they get that formula. Anyhow, but we're just really evaluating that. We'll get this formula. There's no testing. You'll need to remember the surface area of a cylinder formula. If I run into something like that, I'll try to make sure I give you the formula for that. Anyhow, they substitute those values in for the parts that we don't know, which is the radius and the height of that can, and you can evaluate that. Now, like terms and degree, we're going to talk about degrees of monomials or single terms, and then a degree of a polynomial. This example table illustrates it really well. If we have multiple variables in a term, like this 9x squared y to the third, what you do is add the exponents of the variable. So I have a 2 power and a 3 power, so this is a degree 5 term right here. In this case, the variable here, you got to remember if there's no variable or no exponent on a variable, it's 1. So here I have 1 plus 2 plus 3, which is 6, and so on. This is 1 plus 1, 1, 2, and then if there's no exponent, it means that that is to the 0 power. Anything to the 0 power is 1. So I could say this is 7x to the 0 power, which is 7 times 1. Well, the degree of the polynomial is the highest degree of any term in there. So in this case, it's this one right here, which is 6. So the degree of this polynomial right up here is 6. Now, some of the reasons that we do this is to try to find a standard way to write the polynomial and some other things, but I don't know, mostly I think it's really to make sure you're paying attention to the exponents and know what to do with those. Now, if we try to combine like terms, I might find like terms in a lot of different ways, and it's really good to understand what's the goal of this. What I want to use is the distributive property, so I can get something where I can get some constants, just some numbers in the parentheses, so I can perform that operation of subtraction or addition. So like in this case, we have 9x squared y. Now this 3xy squared is not a like term. I can't factor out the variable portion of these two parts here. They're not the same. But this one right here, x squared y and x squared y is. So we change the order. I would prefer that we go to addition because we can use the commutative property in addition. But they're assuming you understand that and make sure you keep your terms and have the right sign. So they rearrange this to be 9x squared minus 5x squared, which then they can factor out the x squared y right here and get 9 minus 5 times this. And then this xy squared and xy squared, same thing. And it's really a strategy of using the distributive property. We actually used them all, our laws right there, commutative, associative, and distributive. And the shortcut word for that is to combine like terms. And what they're trying to do is that hopefully by this point in algebra you can do this. Probably go directly to this step and realize that, hey, these are like terms. 9 minus 5 is 4 times x squared y. 3 plus a negative 1. Though I see a lot of errors here as you forget that there's a negative 1 of that, which is then ends up to be 2. Here, so it's a practice in really understanding how I can use the distributive property to simplify these longer or more complex polynomials. Addition and subtraction are pretty straightforward, same stuff about combining like terms. Probably the place I see errors again is when we're subtracting a group, like in example 6 here. You got to remember that this is really the opposite of this whole grouping here. What's in this parentheses? Well, opposites of are the same as multiplying by negative 1. So I could say this is plus negative 1 times this entire thing. And I think if you practice that a few times this way, you're probably going to make a lot less errors around this subtraction stuff. Because I need to distribute that negative 1 multiplication to every one of these terms. And so the error I see a lot of times is we only distribute the negative to the first term and forget about the rest of these and leave them the same. A lot of errors around that, so don't do that. So this is really the opposite of each one of these terms. If I want to get rid of these parentheses and deal with it as an addition, even though they still write subtractions in here. So this is minus the 4x squared y. Well, minus a negative 6x cubed y squared is positive, and so on. It's the opposite sign, opposite sign, opposite sign. Okay? Now when it's addition, we just combine like terms. So you're looking for ways to use the distributive property to get the constants in a way that I can add or subtract those. Now multiplication is really easier process. It's just using the distributive property. They show this up and down multiplication like we do on paper if you have multiple digit numbers that you're multiplying. It's the same thing. As I take this first term and I multiply it times each term, or in other words distribute, and then they take this term, distribute, they're just showing it up and down. This is a nice way to organize your work, and then you can match up your like terms as you're writing down the multiplication. So pay attention to the like terms, put them in the same column, and it can organize your work to make the addition of like terms. So pretty straightforward stuff. Now, this isn't really talked about, but probably this is one of the most important parts about this section. They don't have an explanation of this. They just show us some examples of what can happen in this this world of stuff that we've covered with multiplication and combining like terms and all this kind of stuff with more complex polynomials. So in this first one here, and this is really about strategy. It's kind of like if you were playing basketball, you can learn to dribble. You probably learn to dribble with your strong arm, or which if you're right-handed, it would be your right hand, and then it's a good strategy to learn how to do it with your left hand, which is really not anything new as far as a concept of drilling. It's just practicing it another way, right? And so very, very much similar to this, what we're going to apply in these examples here. And I would say this page of your book right here, whatever this page is, page 282, you know, if you're going online, while you're doing your assignments, you should probably bring this up, especially when you get into these further examples, and look for this to help use a good strategy to deal with simplifying some of these multiplications and additions. This first one is FOIL. We've learned this as if we have two binomials multiplied. I look at this and I say, well, they're all different terms and those kind of things. Probably the only thing I can do is FOIL. And reason FOIL is pretty good. Strategy is these two inner terms, the outer and inner multiplications that happen end up bringing your like terms together. In other words, first times first, outside times outside, inside times inside, last times last, okay? And then we get some like terms that we can combine. Now they're bringing in special products that we covered last section. Very important to get familiar with this. You want to use these shortcuts whenever you can, and I think if you use this every time you see a squared binomial, hopefully you'll remember this pattern that occurs, is that we take the first term squared, we multiply these two terms times each other and double it. That's what happened right here, to say it in English words, or 2 times first term times last term, second term, and then it's the last term squared. This pattern is very important when we get into factoring, and also we'll show you a couple other ways. Well, I don't know if it's really not a different pattern when we have subtraction, because if I take a cubed times a negative 7a squared b, I get negative 14 a to the 5th b, right? Same thing I really did here, and then I take 2 of them by taking it times 2. This is first term squared, this is last term squared here, so on. It's really the same thing, they just want to make sure you don't mess up on sign, which happens a lot. It says using rules for exponents, okay? Is we can apply these shortcuts we've used for these things, like 7a squared b, all squared is 7 squared a to the 4th, which is 2 plus 2, b to the 1 2 times 2, excuse me, and b to the 1 is 2 times 1. Okay. So apply those rules that we've run into, and that, again, very key is build on how we're building this chapter of tools to put together and shortcuts, and use them. And if you use them every opportunity you have during your homework, you're probably going to remember that stuff for a test. Now, this one here, let's look at this. It says, using the commutative law for addition. Look at this original here. We had this plus this, right? Or times this, excuse me. What they do is really they just say, if you really look at this, and if I change the order of these things and, you know, protect my sign by this is 5t minus 2x cubed y squared times the quantity 5t plus 2x cubed y squared. Hey, this is difference of squares. This is a special product, and boy, when you see difference of squares, I would rather do that in FOIL. It's going to save you a lot of time and a lot of errors. So when I have this pattern, that difference of squares, it's the first term squared minus the second term squared right there. Now, here is a very, very useful thing. Because difference of squares is such a nice thing that when it comes out, we should look for opportunities to make that happen. And in this case, it's a little more complex. But they notice something here that I got 2x plus 3 minus 2y times the quantity 2x plus 3 plus 2y. They notice that, hey, this first addition is the same as this first addition, and then it's subtracting the second part. Well, I could group this together and say that this minus this times this plus this is the difference of squares. So I group these using basically the associative property first on this addition, and then I have, because they're double, you know, they're the same on both, I have a difference of squares situation. You know, they show the a is here and so on. This is very, very useful to doing and simplifying this stuff. If you use the distributive on this, you could get to this point, but you're going to add about 4 extra steps to solving this, which is 4 times as much chance for error. So, well, in this case they say, well, then difference of squares is this squared minus this squared, right? Well, this is a binomial squared, so I'd use that pattern up here for binomial squared, right? And again, apply the rules here. So it's first term squared, 2x times 3 doubled is 12x, and then 3 squared is 9, and then it's subtracting this squared, which is going to be 2 squared y squared, or 4y squared. This, boy, when you can identify this and work, it's going to save you a lot of time, a lot of chances for error. So look for these opportunities. So, and really probably if you see a trinomial or 3 term times 3 term, there's probably something up in that, especially in here. It gets a little tougher later when we have different ways to dealing with trinomials. They're going to bring in some other things that we just have to distribute that multiplication over. So good luck with that. Look for that last example. That's probably the most complex part of this section. Again, I can't emphasize enough to apply all these shortcut rules and do this. Use your powers of powers and all these things that we've covered so far. And practice those as you do this work. There's other ways to do that. If you find yourself doing it a long way to get around some of this stuff, you're not really practicing the way you need to succeed here in the next chapters, especially when we get into factoring more. So good luck with that, and talk to you later.